Hi all, welcome back to the course on quantum mechanics. So we are going to start new module today. It's called the formulation of quantum mechanics. So in the last module, we have discussed in detail about the mathematical formulation of quantum mechanics. So there we have learned the mathematical techniques which is required for the formulation of quantum mechanics. Okay, so this is the overview of this particular lecture. So we'll have the introduction about the scientific methodology first. Then we'll give a brief introduction about the formulations of quantum mechanics. And thereafter, we'll discuss the different postulates in the formulation of quantum mechanics. Okay, so we know that any scientific methodology has a certain step, or the methodology of science has the certain procedures to follow. The first one is, in order to start any theory, any scientific theory, we should have a postulate. Okay, and postulates are nothing but the a priori assumptions. For example, in case of Newton's law of gravitation, the existence of free particle or the existence of point particle is an assumption. Okay, so in practice, there is no, will not get any particle with zero volume, or we cannot get a point particle. But this is an assumption which is required for the building up of the Newton's law of gravitation. Okay, so this is basically an assumption which is built upon, which is required to build the theory. Or in case of kinetic theory of gases, we assume the gas is a collection of the point particles, or the gas is a collection of particles. That is an assumption. Okay, so this a priori assumption is called the postulates, and which is the starting point of any theory. There is no need of proof for postulates because they are just assumptions. We are just taken it as a granted, it is correct. Now, by assuming those are correct, we build the theory. Okay, so any theory or any formulation of any scientific theory will have certain postulates. And once the postulate is ready, we'll have the mathematical formulation based on those postulates. For example, in case of gravitation, we have the existence of point particle, and we can derive, or we can give the equation of force between 2 point particles is given by F equal to G m1 m2 by r square r cap. So these are the force of attraction between 2 point particles. Okay, so the mathematical formulation is the second step. So first is postulate, which are just assumptions, and second is a mathematical formulation. And once you have the mathematical formulation, then we can have predictions. Okay, so certain, so this is the usual way of doing things. So we'll predict new phenomena. And once, if you predict the new phenomena, then we can have the experiment to verify those new phenomena. And once the experiment verifies the predictions, that means the entire step is correct, your postulate is correct, your mathematical formulation is correct, and this entire thing will become the theory. So this is the standard, the scientific methodology or methodology of science. We'll build up with certain postulates, and from the postulate we'll have a mathematical formulation, then a set of predictions and experiments to verify it. Now the another way is, if you have the certain observation which is unable to explain by the present theory, then we'll have new postulates and new mathematical formulation, and we'll explain the unexplained observations. For example, the black body radiation. So the theory of black body radiation developed by the Max Planck, it is another way, because he has postulated something. The postulate was the absorption and emission of the energy by the harmonic oscillator in the form of quanta, and it is only the multiples of h cross omega. So that is the postulate he has made, and from that postulate he has built up the mathematical formulation, and he could be able to explain the observed the black body phenomena, that is the spectrum, the energy spectra of energy density spectra of black body radiation using his postulate, and that becomes the theory of black body radiation. Okay, so either we'll predict the new phenomena or we'll explain some certain unexplained phenomena. That is also a way of the scientific methodology. Okay, so this gives the brief idea about how a scientific method has to follow, or how a scientist has to follow to build up new theory. Now, if your experiment did not prove, did not verify the predictions, then you have to rework on your postulates. Or if your this mathematical formulation could not able to explain the present phenomena, then again you have to rework on the postulates. Then these the steps will repeat. Now we can go to the present scenario, which is our quantum mechanics. Now there are different formulations for quantum mechanics, namely the wave function formalism, the matrix mechanics, the path integral formalism, phase space formalism, density matrix formalism. So there are 9 different formulations available for quantum mechanics. Okay, but in our course, we are mainly dealing with two quantum mechanics, two formulations of quantum mechanics, namely the wave mechanics, which is developed by the Schrödinger, and the matrix mechanics, which is developed by the Heisenberg. And Dirac combined these two mechanics in one umbrella. It's called the Hilbert space formalism. So we'll be mainly discussing about the Hilbert space formalism in our course. And this particular module, the formulation of quantum mechanics, actually dealing with the Hilbert space formalism of quantum mechanics. So we are not going to discuss about what is Hamilton-Jacobi formalism and what is second quantization formalism. So all those things we are not going to discuss in our course. We'll be focused only on the Hilbert space formalism. Okay, so any formalism or any scientific methodology has to start with certain postulates. So the postulates of the Hilbert space formalism has to start with certain undefined notions. Okay, the undefined notions basically motivated by our previous experiences. So in quantum mechanics or in Hilbert space formalism, the main undefined notions are system, state, and observable. So these are the undefined notions. So based on our postulates are built upon. So we can directly go to the postulates of quantum mechanics or the Hilbert space formalism. So the first postulate, which is dealing with the system and state. So it states that to every physical system, there corresponds an abstract Hilbert space. So a system is mapped to a Hilbert space. So corresponding to every system, there is a Hilbert space. And the second is the state of any physical system is specified at each time t by a state vector psi of t in a Hilbert space. So there is a state of the system is represented by a vector in Hilbert space. Okay, so these are the first postulate. Okay, now if you look at the classical mechanics, now state is set of generalized coordinate and generalized momenta, and those are dynamical variables. Okay, so in classical mechanics, the state is represented in terms of the dynamical variables, generalized coordinates and generalized momenta. It can be position and momenta, or it can be angle and angular momentum, etc. Whereas in quantum mechanics, the state is an abstract vector, isn't it? Okay, so in classical mechanics, state is simply generalized coordinate and generalized momenta. Okay, so if you have a one-dimension system, so generalized coordinate q, generalized momentum p. So this point will have some generalized coordinate q1, generalized momentum p1. So this represents the state of the system. Now this particular graph is called the phase space. So in classical mechanics, the state of the system is represented as a point in a phase space. Okay, so Q1 P1 is one possible state. Q2 P2 is another possible state. Okay, so suppose the present state is Q1 P1 and future state is Q2 P2, then there will be only single trajectory connecting these two, the Q1 P1 Q2 P2. So this trajectory actually represent the evolution of state. So the evolution of state in classical mechanics can be represented as a trajectory in a phase space. Now, what is in quantum mechanics? So if you go to quantum mechanics, state is a vector in Hilbert space. So consider a two-dimensional Hilbert space. Okay, so consider a two-dimensional Hilbert space. Okay, again, we have some basis vector ket phi 1, some other basis vector ket phi 2, and the state you can represent it by some vector in this Hilbert space. Okay, so this is the representation, the pictorial representation or graphical representation of state in quantum mechanics. It's a vector, whereas in classical mechanics it is a point. So classical mechanics, state is a point in phase space, whereas in quantum mechanics, state is a vector in Hilbert space. Now the classical mechanics is completely a deterministic science. That is, once you know the present position and present momentum, you can predict the future position and future momentum, as well as the past position and past momentum. So your entire the past and future are there in the present state of the system. And only thing you have to know is the equation of motion. It is how this generalized coordinate and generalized momentum evolves with time can be known once you know the equation of motion. Maybe the Newton's second law of motion, or the Hamilton's equation, or Lagrange's equation. So better you have to, when you're going to discuss phase space, we'll use the Hamilton's equation. That is the equation for Q dot, which is dot h by dot p, and P dot, which is minus dot h by dot q. Okay, so these are called the Hamilton's equations of motions. So once you know the Hamiltonian, then we can find out what is your future position and future momentum. That is future generalized coordinate and future generalized momentum. Once you know the present state of the system. So this classical mechanics is completely deterministic. Okay, and it is the state is represented by a point in the phase space. And whereas in quantum mechanics, the state is represented by a vector in the Hilbert space. Now, whether it is deterministic or not, that we are not going to say at present, that we'll discuss later. Okay, whether it is deterministic nature or the probabilistic nature, that we'll discuss later. That is, whether you can you able to predict the future state of the system in quantum mechanics once you know the present state. That we cannot answer now. That will answer later. Okay, but in classical mechanics, that is well known to us. It is a deterministic science. If you know the present, it is possible to find the future, and it's also possible to find the past. Okay, now any arbitrary state vector or any arbitrary vector is a superposition of basis vectors, isn't it? Okay, so consider again, you consider a two-dimensional Hilbert space. Okay, two-dimensional Hilbert space. So graphically, we can represent like this. We have a ket phi 1 and ket phi 2, some vector psi. Now we can write this ket psi is a superposition of phi 1 and phi 2. So this is called the decomposition of vectors. So you can expand any vector in terms of the basis vectors. This ket phi 1 and ket phi 2 are just basis vectors. So we have expanded the ket psi in terms of the basis vectors. Okay. Now we said that the state is represented by a vector in Hilbert space. So that means any vector in the Hilbert space is also a possible state, isn't it? So this ket phi 1 is a possible state. And ket phi 2 is again a possible state, is another possible state. So this ket psi we have write in terms of ket phi 1 and ket phi 2. So phi 1 is a possible state and phi 2 is a possible state. So the superposition of phi 1 and phi 2 is another possible state. So this is what is called the superposition principle. The superposition of two states can be another possible state. Or you can expand the state, a state in terms of another state. That is what is called the superposition principle. And there is no such superposition principle in classical mechanics. So if you look at classical mechanics, the state, if you look at classical mechanics, the state is just a point in the phase space. Okay. So if you add two states, then that will not give a possible state. So in classical mechanics, there is no superposition principle. There is no superposition principle, but you might have a confusion. That is, in classical mechanics, we are dealing with waves, whereas in waves we use the superposition principle. That is true. So in waves we can use the superposition principle until the wave equation is linear. Okay, in general, the wave equation can be non-linear also. So in those cases, we cannot use the superposition principle. Okay, so the classical mechanics, we use the superposition principle only in case of wave, only because the wave equation is a linear equation. If the wave equation becomes a non-linear one, then we cannot use the superposition principle. So the superposition principle is not true in general in classical mechanics. There are only some special cases, that is only in case of wave, we can use the superposition principle in classical mechanics. But whereas in quantum mechanics, the superposition principle is valid always. The main reason is the equation of motion in quantum mechanics is a linear equation that we'll discuss later. Okay, so all the equations in quantum mechanics, all the equation of motion in quantum mechanics is a linear equation. So that is why the superposition principle is valid always in quantum mechanics. And the other thing is in quantum mechanics, in classical mechanics, we can have a linear system or non-linear system. For example, if you have a harmonic oscillator or an harmonic oscillator, so we'll have the non-linearity in classical mechanics. But any linear system or non-linear system in classical mechanics will become a linear system in quantum mechanics. So in quantum mechanics, all the systems are linear because the equation of motion is linear. Okay, so the main thing is this: the equation of motion is linear in quantum mechanics. It's always linear in quantum mechanics. Okay, so whereas equation of motion is non-linear in classical mechanics in general. Okay, so that's all about the discussion of the postulate one about the system and the state. And the thing is, in classical mechanics, that we can write here. So in classical mechanics, we may have linear system and non-linear system. If you go if you go to the classical domain to the quantum domain, the quantum mechanics always have linear system. So there is no nonlinear system in quantum mechanics. All the systems are linear. So whether you found an equivalent nonlinear classical mechanics system to quantum mechanics, that would also be a linear system. So the next, we can go to the next postulate, the postulate 2. The postulate 2 is based on observables and operators. The observables are nothing but measurements. Okay, so this states that the corresponding to a very observable physical quantities, there exists a Hermitian operator. Okay, so for observables, there is a corresponding Hermitian operator. So observables is also called measurements. For every measurement, there is a corresponding Hermitian operator. The next is the only measurable values of physical observables are various eigenvalues of the corresponding operator. So that is the output of measurement would be the eigenvalues of Hermitian operator. So we know that the measurement is always is measuring something using some instruments, and that should give real numbers, isn't it? Okay, suppose if you're measuring temperature, you should get some number. If you're measuring current, you should get some real number. If you're measuring voltage, you should get some real number. Okay, so that is why this postulate is, that is, your observation must be a Hermitian operator. Okay, so this Hermitian character of the operator ensures that the eigenvalues are real. That is, the output of measurements are real. Because this postulate states that the output of measurement are the eigenvalues, and that must be real. Output of measurements must be a real quantity. So for that, your operator must be a Hermitian operator. Okay, so that means the measurement, if you mathematize the measurement is represented by the Hermitian operator in that Hilbert space. Okay, and that Hermitian character ensures the output of the measurement is a real quantity. Okay, so the measurement output, whether you measure temperature or you measure current or you measure voltage or any other quantity, it should be a real number. Now, in order to ensure this real number, the measurement is done by the Hermitian operator, or measurement is represented by the Hermitian operator, and its eigenvalues would be get as output, and that is always real number. Okay, so this is a simple logic. So that is our second postulate. Next is the state vector can be expanded in terms of basis vectors, which can be the eigenvectors of Hermitian operator. So for each eigenvector of Hermitian operator, there will be a corresponding eigenvalue, which are the observables or dynamical variable. So thus, the state vector can be identified in terms of possible dynamical variables. Okay, so earlier we have stated that in classical mechanics, the state is represented in terms of dynamical variables such as generalized coordinate and generalized momenta. And that kind of thing is also possible in quantum mechanics as well. Because what it says state is the state vector can be expanded in terms of the basis vectors. Okay, so better we can have an example. So we'll have an example I will write here. So consider we are measuring the spin of electron. The spin of electron. The spin, there is the spin of electron, this measurement we can represent by Hermitian operator. So spin, I am going to denote it as SZ. Now the possible eigenvalues of these Hermitian operators are plus h cross by 2 and minus h cross by 2, and corresponding eigenvectors I can represent as ket plus and ket minus. Okay, so that is that for each eigenvector of Hermitian operator there will be corresponding eigenvalue. So for ket plus, the eigenvalue is plus h cross by 2, and for ket minus the eigenvalue is minus h cross by 2. Okay, so there's a state vector can be defined in terms of possible dynamical variable. Okay, so this ket plus is a possible vector and ket minus is also another possible vector. Okay, so consider a system of single electron. The eigenvalues of spin angular momentum operator are plus h cross by 2 and minus h cross by 2, and the corresponding eigenvectors represented as ket plus and ket minus. So that means the SZ acting on ket plus would give plus h cross by 2 ket plus, and SZ acting on ket minus would give minus h cross by 2 ket minus. So therefore a general state we can represent it as a superposition of ket plus and ket minus. Okay, so the state of this electron I can write as some coefficient times ket plus plus some coefficient times ket minus. So C plus is a coefficient corresponding to ket plus and C minus is a coefficient corresponding to C minus. Okay, so what you have done is I have expanded your state in terms of the dynamical variables. So this ket plus, or it represent the spin up state, and ket minus represent the spin down state, and those are the dynamical variables, the spin up and spin down. And I can write, I have written your general state psi in terms of these dynamical variables. Okay, so that is possible. So if the electron is completely in spin up, I can represent the state as ket plus. If the electron is completely spin down, I can represent it as ket minus. Okay, now this is also called the superposition principle. This ket psi I have written is a superposition of ket plus and ket minus. Now we cannot say that in which state this electron exists. So this electron now it is existing is a superposition of ket plus and ket minus, isn't it? Now if you act or if you measure the spin of the electron in this general state, then the result of that measurement will give either plus h cross by 2 or minus h cross by 2. We'll never get both. So what it's meaning? So if general state is this, the ket psi is a superposition of ket plus and ket minus, then the measurement of spin you will get either plus h cross by 2 or minus h cross by 2. So that means the act of measurement collapse the state vector to one of the eigenvector of that operator. So the vector psi is either going to ket plus or it is going to ket minus when you measure the spin. So if you measure the spin on ket psi, there are two possibilities. We'll get the result as either plus h cross by 2 or we will get the result as minus h cross by 2. So that means either this ket psi transforming to ket plus or the ket psi collapsing to ket minus. So this is called the collapse of state vector. And present we don't have much details about how the state vector collapse to one of the eigenvector, but that is true. And it is the result of our second postulate. The second postulate states the only output, the only measurable output of a measurement are the possible eigenvalues of an operator. And if you get, you will get the eigenvalues of an operator once the vector is in that eigenstate. Okay, so if you're measuring the spin, if the state of the electron is in ket plus, we'll get plus h cross by 2. If it is in ket minus, you should get minus h cross by 2. And that is what is happening here. when you measure the spin on kit psi, you're getting either plus h cross by 2. That means the state must have collapsed to kit plus, or will get minus h cross by 2. So if you're getting minus h cross by 2, that means your kit psi must have collapsed to kit minus. So this is called the collapse of state vector. And at present, we don't have much information about how the state vector collapse to one of the state vector. That is not known to us, but this is true. Once you measure it, it will collapse to any one of the state. Okay, so this so the two things we have discussed now from the postulate 2. The one is you can express your the state in terms of dynamical variables. So you can represent the state in terms of either kit plus and kit minus. So that is possible with this uh, postulate. And the second one is once you measure any dynamical variable to a general state, then that state will collapse to one of the eigenstate of that operator. So this is a simple example for the spin. Suppose if you are measuring the position, or if you are measuring the momentum, what will happen is the state vector will collapse to, if you are measuring momentum, the state vector collapse to one of the eigenvector of that momentum operator. Now, if you are measuring the angular momentum, the state vector will collapse to one of the eigenvector of the angular momentum operator, and so on. So what would be the measurement? Once you measure on the system, then the system might have been in some state in originally, that will collapse to one of the eigenvector of that particular operator. Okay. Now, if the electron is in one of the eigenstate, for example, if kit psi is simply written as kit plus, that means it is certainly in the spin up state. So the measurement of spin will give plus h cross by 2. Okay. Similarly, if the state of the system is represented as kit minus, then we'll get the spin as. So for that, we can have an experiment called Stern-Gerlach experiment. Okay, suppose you are passing a beam of electron through a non-uniform magnetic field. So we have some magnetic field here. Okay, so if it is passed through a non-uniform magnetic field, this will split into two categories, two paths. So one contains spin up, only spin up, and other one contains only spin down. Okay, so spin up and spin down. Now, if you measure, so this is actually a measurement. So originally, the state psi is a superposition of kit plus and kit minus. So some of the electron passing through this Stern-Gerlach setup will move the upward, and this upward electron will be in the spin up state, and the some electron will move in the downward direction, that would be in spin down state, represented by kit minus. Now suppose if all the electrons are in spin up, then there will not be any the lower trajectory, downward trajectory will have only upward trajectory. All the electron will move in the spin up. And similarly, if the electron is completely if it is completely in spin down state, then there will not be any upward trajectory. All the electron will move in the downward trajectory. Okay, so that is what it's meaning. Okay, so here there is no need of collapse, because if it is purely in the eigenstate, then if the system is purely in the eigenstate of the operator, we'll get the corresponding eigenvalue as a result. There is no confusion in that. Okay, so whereas if it is not in the eigenstate, if it is a superposition of eigenstate, then we'll get one of the eigenvalue as the result, and that will vary. Okay, suppose if you as we have discussed earlier, suppose the system is in the superposition of both spin up and spin down, then some electron will go to spin up, that is in the upward movement, and some electron will move in the downward movement. And we cannot predict which electron will move in upward direction, which electron will move in the downward direction. That is that we cannot predict. Okay, but that would happen. So physically it happens, some electron will go to spin up and some electron will go to spin down, but we cannot able to predict it which electron will move in which path. So it is completely unpredictable. Okay, again there are certain more repercussions of the postulates too. So consider two operator A and B with eigenvalue set AI and set BI. It is operator A has eigenvalue A1, B1, A1, A2, A3, etc. And B has eigenvalues B1, B2, B3, etc. Okay. So then once you measure operator A, then what will happen? The state becomes one of its eigenstate and gets corresponding eigenvalue AI. Suppose the operator A has eigenvectors get phi I and corresponding eigenvalues are AI. Okay, then a general state psi we can expand as C1 get phi 1 plus C2 get phi 2 plus etc. Cn get phi n. Okay, now if you measure operator A on psi, then there are many possibilities. So either this get psi will collapse to phi 1, or it will collapse to phi 2, or it will collapse to phi 3, up to it can collapse up to phi n. So if it is collapsing to phi 1, then we'll get the eigenvalue, the result of the operator as A1, because the corresponding eigenvalue is A1. If the vector is collapsing to get phi 2, then we'll get the eigenvalue as A2. So that is what is I have written here. So once you measure operator A, the state become one of its eigenstate and gets the corresponding eigenvalue as a result. Okay, so next, if you measure ket B, then the state jumps to one of the eigenstate of ket B and gets some eigenvalue Bj. How is it? Because this ket B can have some other eigenvector. Okay, so suppose the chi I is the eigenvector of operator B corresponding to the eigenvalue Bi, chi I. Okay, so let us suppose the action of operator A on psi gives collapse the vector into ket phi 2, and we have got the corresponding eigenvalue ket phi 2. So then the operator B has to act on this ket phi 2, because we have got the eigenvalue A2 as a result. So that means the system is in the state ket phi 2. Now we have to act B on ket phi 2. Now we have to act B on ket phi 2. Now this ket phi 2 can be expanded in terms of chi I. So this ket phi 2 I can write as some d1 chi 1 plus d2 chi 2 plus etc. dn chi n. Okay, so in general, this chi1, chi2 up to chi n is also a basis vector. So therefore, this kit phi2 can be expanded in terms of the basis vector. So therefore, the action of B on phi2 can lead to different results. So we may get chi1, or we may get chi2, etc. We may get chi n also. So if you're getting chi1, we'll get the eigenvalue b1, or we'll get eigenvalue b2, and up to eigenvalue bn. So you may get the different the possible eigenvalues. So there are different possibilities. Okay, so we cannot predict at which eigenvector that will collapse. Okay, so this would happen if A and B do not commute. So if A and B commutes, then both will have the same set of eigenvector. Then there is no such problem. So if A and B do not commute, then the operator A would give some eigenvalue, and operator B will give some other eigenvalue. There will not be any connection. Suppose if you prepare a copies of this psi. Okay, so the copies means ensemble. So if you prepare the ensembles of kit psi, then if you have first copy, second copy, third copy, and so on. So in first copy, the operator A acting on psi, suppose you are getting the result A2, and on that, if you act operator B, will get suppose you will be getting some result B3. So okay, so in one copy, the operator A gives A2 and operator B gives B3. Now in the second copy, suppose the operator A again gives A2, then operator B may give some B1, or it may give B4. Okay, so that means your the outcome would become completely unpredictable if both the A and B are not commuting each other. Now again, so if you measure operator B on phi2, suppose you are getting B1. Okay, suppose you get B1. Now thereafter, if you measure A again, what would happen? Then what would happen is this chi1 can be expanded in terms of phi, isn't it? So we can expand this chi1 as E1 phi1 plus E2 phi2 plus etc. up to En phi n. Now if you measure A again, then we'll get some other eigenvalue. So we may get A1, it may collapse to phi1, or it may collapse to phi2, or it may collapse up to phi n also. So that is the problem here. There is you are acting the same operator on the same system, but at different times you'll get different results. Okay, so better I will summarize here. Suppose you have some state psi and A acting on psi. You suppose you get A2 as eigenvalue. Okay, so you measure operator A, you got eigenvalue A2, and after that, if you measure B, suppose you got the eigenvalue B1, and thereafter, if you measure A again, you may get some other eigenvalue A3. So you are measuring the same operator, but in between you have measured some other operator. Then in each measurement, you will be getting different results. So this is basically due to the superposition of the state vectors. Because one state we can expand it in terms of the another state vectors. And the result of any observation is the eigenvalues of that corresponding operator. So that means your operator, the vector must be collapsed to one of the eigenvector of that operator. So this is the case if the A and B do not commute. So this is the case if the commutator AB is non-zero. Now what would happen if the commutator AB is 0? So suppose the both operator A and B are commuting. Then again, the measurement, suppose the general state is psi. the measurement of operator A, suppose you get A2, then the measurement of operator B will give the eigenvalue B2. Then the measurement of operator A would give the eigenvalue A2 again. Okay, so whatever be the order of the operation will get the same eigenvalue again and again. What is the reason for it? Because if two operator commutes, they will have the same set of eigenvectors. That means the A on phi I gives AI get phi I, and B on phi I gives BI get phi I. So they will have the same set of eigenvectors. So initially the state is psi, and you acted A on it. Then psi will either collapse to phi 1, or it will collapse to phi 2, etc. It can collapse up to phi n, and we'll get the corresponding eigenvalue A1 or A2 up to AN. Suppose this is what has happened. The state is collapsed to phi 2. Then you are going to measure operator B. Now the phi 2 is also the eigenvector of operator B, so therefore it will not change. So B on phi 2 will give B2. Okay, so there will not be any collapse of operators, collapse of state vector. The vector will remain in phi 2. So B on phi 2 would give B2 phi 2. Then you act the operator A. Again, the vector is again is in the same phi 2. Then the operator A would also give the same result A2. So that is the thing. So if you have two commuting operators, then that this particular phi 2, this the state phi 2, will get the eigenvalue A2 P2. Okay. Now, if you have a collection of all commuting operators, suppose A, B, C, D, etc. So all these A, B, C, D are the commuting operators. Then the first measurement of A will collapse to the one of the eigenvector of operator A. That would also be the eigenvector of operator B, C, D, etc. So therefore, the measurement of operator A will give some eigenvalue corresponding to A, and then the measurement of operator B would also give the eigenvalue corresponding to the same eigenvector. Then operator C would also give the eigenvalue corresponding to the same eigenvector, and so on. So then for that state, okay, so if you have some get psi, if you act operator A, this will collapse to the get phi 2. Then get phi 2 would give the eigenvalue A2. Then measurement of B would give B2. The measurement of C would give C2, etc. So therefore, this get phi 2 we can write as get A2, B2, C2, etc. So that means the state of the system you can write in terms of the dynamical variables. So remember, these eigenvalues are nothing but the dynamical variables. These are the results of measurements. Okay, so this eigenvector I can represent in terms of the dynamical variable, or the state we can represent in terms of the dynamical variable. So the best example is the hydrogen atom problem. Okay, now we have to define one definition. So this collection of all commuting operators are known as the complete set of commuting operators. In short, it is called CSCO, complete set of commuting operators. And the eigenvalues of complete set of commuting operators are called compatible variables. And we can assign the definite values for each dynamical variable that eigenstate, because these the compatible variables are definite for that particular state, and we can assign the eigenstate in terms of these compatible variables. Okay, so the simple example is a hydrogen atom problem. So in hydrogen atom problem, the Hamiltonian, the square of angular momentum, the z component of angular momentum, the z component of spin, all these are commuting operators. So these are the complete set of commuting operators, and the corresponding eigenvalues are energy, angular momentum, the z component of angular momentum, and z component of spin angular momentum, etc. And it can be represented in terms of the quantum numbers, the principal quantum number, the angular momentum quantum number, the azimuthal quantum number, and spin quantum number. There is n, l, m, s, etc. And therefore, your state, an eigenvector, I can represent as ket n, l, m, s. That means you are the Hamiltonian acting on ket n, l, m, s would give E n, n, l, m, s. This E n is nothing but the eigenvalue of Hamiltonian is called energy eigenvalue. And for hydrogen atom problem, it is minus 13.6 by n square electron volt. And L square acting on n, l, m, s. So this L is corresponding to the eigenvalue of L square. So this would give L into L plus 1 h cross square n, l, m, s. And if you act Lz acting on NLMS would give MH cross NLMS. So there are certain connection between L and M. Okay, so here N can run from 0, 1, 2, 3, etc., not 0. 1, 2, 3, etc. And L corresponding to 1, 2, 3, etc. up to N minus 1. And M can run from minus L to plus L, and S can have plus 1 by 2 or minus 1 by 2. These are the possible quantum numbers, and these are the dynamical variables. And in terms of these dynamical variables, we can represent the state. And this state is the possible state of hydrogen atom problem is the eigenstate of the complete set of commuting operator. And this state is also called the stationary state of hydrogen atom. Okay. So next we can go for the postulate 3. I think it is better we can stop it here. The postulate 3 we'll discuss in the next class. Okay. So we have two postulates today, which is the postulate 1 based on the system and state, and the postulate 2 is based on the observation. The postulate 1 states the state is the system is represented by a vector in the Hilbert space, and the state is represented okay, the system is just a Hilbert space, and the state is represented by a vector in Hilbert space. And the postulate 2 states all observation or all measurements are represented by an operator and a Hermitian operator in the Hilbert space. And the result of individual measurement, the individual observation, are the possible eigenvalues of such operators. So that will gives a new phenomena called the collapse of state vector. And as the discussion we have discussed about the possibility of the result of commuting operators and non-commuting operators, etc. And it is possible to represent the state of a vector in or the eigenstate of an operator in terms of the dynamical variables, or in terms of the eigenvalues of the corresponding operators. Okay, so with that, we can stop this particular lecture. We'll continue this lecture with the postulate 3 in the next class. So thanks for watching this video. So we'll going to discuss the postulate 3 next class. So see you soon. Bye.